Swayam Prabha. Digital India. Educated India.
Okay, now we discussed various uses of elastic pairs. Now let us actually try to model their stiffness. Okay, so that is, let us look at the details of these flexures. Let us begin with circular notch flexure. That is, if I have these circular notches like this, there is again a relatively rigid part there, related part here, and we are saying that this is fixed. Okay, and this can be a very big one that is going to rotate. Okay. When we do that, what we want to know is, if I were to model this, that is this entire portion is what we call circular notch hinge with an equivalent. So, if I were to draw again like I had drawn earlier, we have this rigid body here and there is a frame. Now, I would like to model by putting a hinge there, because that is the effect of rotation and a torsion spring. I want to know what this kappa is. This is the torsion spring. It is a model constant. Okay. This has been done by various people over the last I guess more than half of the century, starting from 1960s to now. Even now papers are published on how to get this kappa as accurately as possible. Of course, we have finite element analysis to analyze this, but that may not be suitable when you try to design, because you have many elastic pairs in a complicated precision compliant mechanism, and if you know a simple formula for this kappa, torsion spring constant, then one can use it to design these mechanisms. Okay. So, there are three methods, actually one can say many more methods. The three methods. The first one is to use the beam equation. Okay. You can think of this one. So, what I have hatched here, this whole thing is like a beam of variable cross section. Normally we take a beam to be uniform cross section, but you have variable cross section beam and it is deforming. When I say that this is getting some rotation, it is because this beam, so called beam, it may not satisfy all of beam theory's assumptions, but it can still be modeled as a beam. These are all approximate, as, or I would even call empirical, based on whatever measurements that you do and lot of approximations that one do. These are approximate formulas using beam equation, and you basically integrate this beam equation with variable cross section. So, here if we recall the beam equation, this will be Young's modulus E, second moment of area I, and if I say W, the transverse displacement of this beam, double prime, that is d square W by dx square, and then double prime, and you can put the Q, that is the transverse load or moment. If you were to take integration twice, you can also write it in terms of the bending moment. This is a transverse load. Okay, now this I is the one that is variable, it is a function of x. So, you can take that here and integrate and try to see how much rotation you get at this point, and based on that you basically come up with the equivalent torsion spring constant. That is exactly what these two people did. Paros and Weisbart in 1965. Okay. When they do that, they get or they got an expression that looks like this. What is rotation for alpha z mz. So, what they are actually showing here is alpha z, that is the rotation about the z axis. So, that is z axis here is going to be out of plane over here, out of plane. Okay. So, so that one alpha z, they are relating to mz equal to some large expression that you see here. It may look formidable, but the idea is simple. They are taking the beam equation, simply integrating for the variable cross section with lot of approximations. Even after that, it is this big, okay, where beta is T by 2 r and gamma is 1 plus beta. What is T and r? Let me show it here by drawing this flexure. So, when I have a flexure like this, of course, r is the radius. So, this is the radius of the flexure and this distance is T. Okay. And of course, this is the rigid portion that is on both sides. This is T and r, which is in beta, and gamma depends on beta. So, everything depends on T by r, but also you have B, which is out of plane, right. So, it is going to be like this here. And this is B that you see in the formula. E is of course Young's modulus, and R I said radius of that notch, and then you have beta, gamma, various trigonometric quantities and square roots and 3/2s and all that, right. It is a long formula, but obtained by integrating the beam equation. Okay. So, what is actually getting here, this expression, inverse of that is kappa that we want, because the kappa that we want should be relating mz to kappa here, and the angle in this particular case it is shown with alpha z, rotation about z axis. So, this one is 1 over this expression, the way it is written, okay, very long, and while it is easy to put numbers into it and get this kappa value, in terms of design, what thickness T you should have here, what R, what B, it is not that easy here. I think B is the one that comes out and R, but then this ratio T by R is everywhere in nonlinear fashion. This is the long version of Paros and Weisbart formula. They got not only this rotation stiffness about the z axis, out of plane axis, they also got transverse thing here, the delta y, meaning that the same flexure. So, let me draw it again. This is the base, it is fixed here, and there is a rigid body, right. Now, when apply not moment or torque here, when apply a transverse force, okay, I am calling it Fy, meaning that this will be x here, so that becomes y. Fy, how much does it move? Okay, it is going to move a little bit. That is your delta y. That also has a long expression. So, now we have beta, again what you had earlier, gamma, but also some other theta m is here for circular flexures, that is taken as pi by 2. Lot of empirical assumptions that are made in this to get this. Likewise, you can also get the axial, that is again if I were to draw with this one fixed and you have rigid body, if I apply a force Fx here, how much does it move? For that also a rather long formula, because now it is a bar with variable area of cross section, right. So, area of cross section along the x is varying, but that also you can get. So, note that just because these formulae are long, let us not think that it is complicated, it is simple with lot of assumptions, but the work of Paros Weisbart 1965, whatever they had done was very widely used. Even till today people in the industry use it a lot, because they were the first ones to do this, and they were also very clever. They had simplified versions. So, whatever I shown long expressions, now you have the same things in a simplified form. You see, you might ask, where is this 2.57 coming? Why is this 5 by 2? They are all approximation. The long formula for some ranges, they simplified them so that you have. Now, if you have a thing like this, so from here, from this formula, if I want to write kappa, like I said, it should be inverse of this expression. I can write it as 2 EB t raised to 5 by 2 divided by 9 pi and then r raised to half square root of r. Now we can see how kappa changes if I were to change my radius, increase or decrease, at what rate kappa would change, or this t, you see this 5 over 2, I have design insight now. That is why people love such formulae, because they are not accurate in the sense that you may still incur quite a bit of error, sometimes 10%, 20% also, but the range of motion that if you know ahead of time what error it is, you can take that into account while designing this complex compliant mechanism, the elastic pairs. Similarly, for Fy force, Fx force, there are simplified formulae. Okay. So, these are very widely used, but then people are not happy that Paris-Weisbart formulae still hold, but people want to improve. There are a lot of people. So, this top formula here by a person named Lebontio, he used a different method. Paris-Weisbart used basically variable cross section beams and integrated them with lot of approximations, right. Lebontio used energy method, a so called Castigliano's theorems, that is, you would write strain energy, take partial derivative of strain energy with respect to, let us say if you want to get this angle alpha z, you have to take partial derivative with respect to mz, corresponding actuation. If it is angle, there is a moment. So, you take strain energy, partial derivative of the strain energy with respect to this mz will give you alpha z, corresponding rotation, and that is what he has done. He has taken a lot of trouble to derive these expressions lately. This is more recent, not 1965 Paris-Weisbart. So, now he has at his disposal Mathematica, Maple, all these symbolic manipulation things to do, and that is what he does. And he took advantage of these modern tools or symbolic algebra software, so that now it not only for circular flexures, he also has taken elliptical, okay, or it can be corner filleted, something like this, okay, and that can be inside. Now, I am talking about when I say I am only drawing one curve, right, there is other curve, and you can have this, or you can also have things like this, and you can have parabolic, hyperbolic. He has taken every possible curve and he has written an entire book on these approximate formulae by doing lot of manipulations. So, he is basically using energy method to derive this. This one by other set of people, Wu and Zhao, they used a different technique called conformal mapping technique. So, you have uniform beam, we know how to do that very easily. Now, when you have a cross section that is varying, you map these two conformally and you can use appropriate mathematical tools to derive expressions. Okay. So, he also has this alpha z by mz or 1 over kappa. So, now we have Paris and Weisbart, Lebontio's formulae as well as Wu and Zhao, and there are few others. So, there are a lot of approximate formulas, and when there are so many, somebody would write a review paper, and that is what has been done. There is a review paper comparing not for all this elliptical, hyperbolic, all that Lebontio did in an entire book, just looking at circular flexure hinge, what we talked about, such as this. Okay. How do these things compare? It is a very nice review, and they have taken a lot of effort to compare all of these things with finite element analysis results as well. FEA is finite element analysis results. So, they are showing here several names. First one is Paris and Weisbart full, and other is simplified, and then this Lebontio, and then Wu, and somebody called Treslin and Smith. You will hear this name again in this lecture, and Schoolborough. If you see, let us look at Smith one, right, that is these stars, right, it is way off from what we are plotting here is error. Finite element analysis is taken as the gold standard here, and that is perfectly all right. Today we have finite element analysis software that is very accurate by if you take proper care. Okay, that theory has developed very well, and implementation also has reached a stage where you can trust it. So, if you compare with finite element analysis, how do some of them have 50% error, you see this is going to 45% error, right. and some of them are accurate. Let us see which of them is very accurate, that the one with the pluses, somebody called Schoolborough, right, that is seems to be closest to the 0 error. And if you look at Paros and Weisbord, the circle and the square, circle is going like this, full one, and square is like this. So, simplified one is more accurate than the full one, right. So, that probably at that time they did not know, but now when you do it you get these, and some things are going topsy turvy also. This Tresselin, the error is going up and down. So, people have made various approximations to do it, but you can see apart from these the first one which has large error, most of them 10% to on the other side, some of these have 20%. So, plus or minus 20% error is what they give, because they give a simple torsion spring constant to you. There is another thing, this small length flexure. So, when you take now like this, this is fixed, and now focus is on this little thing. So, this is what is the small length flexure, it has small length. For that one we can write using just the simple beam theory, this kappa can be written as EI by L. Okay. So, when you have this thing replaced with let us say a pin joint, let us say I replace this, I will use a different color. Okay, replace with a pin joint, there will be torsion. So, this will become the frame now for this rigid body. Okay, this is the rigid body or rigid segment. Okay, there is a torsion spring, the kappa is given by E, Young's modulus, I second to area, and the L is the length of this flexure. Okay, this has been done by several books in this field, but one other thing that you can do here, you can also get the maximum stress when you are designing. Or likewise Paros and Weisbord and Lavontio and all others have given not only formulae for torsion springs, but also for maximum stress there, which is very useful. Otherwise you have to do finite element analysis, you have rigid segments and narrow regions. So, when you take meshing, you have to have very small elements or take a lot of effort to use different mesh density in different portions of the mechanism. So, if you want to get accurate estimate of stresses, it will take a lot of effort, but these people not only have gotten torsion spring constants, but also have gotten expressions for stress. For example, in this case if you want to get maximum stress, this is just a beam, there is no variable cross, that is why it is one of the simplest cases here. You have the usual MC by I, this is the moment and the second moment of area, this is basically Y max by 2, Y max in this case is basically this, if I have a small length flexure, this is T and this Y max is going to be that, right, or T by 2. So, that is My by I, you remember that is what you can have, right. Here is one other interesting comparison paper. This actually uses dimensionless design graphs. So, this is dimensionless, which is nice because you can make them big and small and whatever material. What they are showing on the x axis, okay. So, on the x axis here they are showing sigma divided by they are giving a sign, psi meaning rotation about z axis divided by that angle psi and then E, Young's modulus. So, stress divided by that angle and Young's modulus. On the y axis they are giving rotational stiffness, where what they are calling the kappa psi psi divided by Young's modulus, the T that we have in that corner flexures, and then H square, that must be R square, okay, radius square, something in that. I think they are showing, what they are comparing is this cross flexure that we had seen, which has strips like this. So, basically small length flexures arranged like this, where this is attached to one rigid body, whereas this is attached to a frame, this one, and then this small length flexure where you have a rigid body and a joint like this. Okay. And here is a circular notch, just like that between two bodies, that circular notch, and it is comparing them non-dimensional way. So, if you say that you have a certain material that you have chosen, then you know this sigma max that you are low and E. If you want to know certain angle of rotation, you go there 0.25 or whatever, then you can see which one of them will be the stiffest, right. There are 3 curves here. So, for each one of them, this dotted one is for the cross hinge, that is this one, and then dashed one is for the circular hinge, and solid line is for the what they call beam hinge or small length flexure. You can do this. Sometimes these design charts are very useful for this type of work. Rather than the long formulae, we have these design charts. And there is another comparison. This one is by Trees and Kota, relatively recent paper in 2000 or so. So, here they are comparing various kinds of these elastic pairs. Okay. Some of these small length flexures here, you can see the images, and this is parallel motion and folded and symmetric, whatever I have shown earlier, and a few new things as well that are there, including this 3-dimensional one. And there is something called a Bendix pair, that is a very interesting one that I will show. And there is a split tube flexures. If you take a tube, okay, let us say we take a tube and have a little split on it somewhere here, then if you attach at one end and then other end, okay, tangentially at 90 degrees apart, between these two you can rotate, and that gives you a very nice flexure equivalent. It is called split tube flexure. There are a number of other configurations actually. Here what they are doing is they are comparing the range of motion. The first one is the range of motion, and other is axis drift, stress concentration, off axis stiffness, and compactness. Sometimes things are very big, right. So, for example, some of these things are very bulky. So, they have used 5 criteria, put them 0, minus, plus. 0 means neutral, minus it's not good, and plus is it's better than the others, right. So, again let us look at the parameter that they have taken to compare. One is the range of motion. Range of motion is limited for most of these, unless you use these flexures, even then it is not a whole lot. Other thing they have taken is axis drift, and that is a very important one. These flexures, when they rotate, their axis is not going to remain the same. That I did not mention, that is a very important thing, and modeling that is quite difficult also. All these formulae do not capture anything, that is why the errors in them is very high, right, sometimes 20% as we saw, right. Axis drift, and then stress concentration, because they are being heavily stressed in narrow portion of the material of the compliant mechanism. Stress concentration is very important. Then there is off axis stiffness. If one axis is very flexible, what about? The split tube flexure was developed because its off axis stiffness is quite good, okay. And compactness, how compact it is, right. So, if I look at the split tube flexure, which is over here, you see a plus sign. Its cross axis stiffness is very good, and stress concentration is also very low, that is plus. Range of motion is quite high, you can go to 90 degrees or more, and other things are neutral. So, some of these that have only pluses, of course, this paper was focused on this particular flexure, it has all pluses and 1 0, it is not compact. Here they have put, even though it is not that compact, they have put all pluses. It is subjective comparison of various joints. This paper is worth looking at. This is by Trees and Kota, Journal of Mechanical Design, July 2005. So, that is Journal of Mechanical Design, July 2005. Okay. It is worth looking at, and these are all the different things that we have made. in solid model and in 3D print, and you can compare lots and lots of elastic pairs are there, which we had already emphasized that they have no specific shape. One can come up with a lot of different shapes and get these things. And this is the Bendix joint that has been commercially available for a long time, very nice joint. So, it has basically plates. I think you can see a plate over here. Let me change the color. There is a plate over here and there is a plate over here, 2 plates cross there. When I play the movie, you will see how it works. Let us the arrow, yeah. So, you can see the plates moving, and this is the side view, how these plates move. They are not touching one another, you get this rotation. It looks very compact actually. They are sold, one can buy them in metal and plastic and lot of different things. It is a very successful elastic pair. Range of motion is not that bad actually in this. Okay. And you also have finite element analysis of all of these different flexures, and like I said, people have compared them quite a bit. And here is one interesting one where we are moving away from simple flexures. Now we can have these beams. Okay. They are still small compared to the rest of the structure. This actually was used by a company called Agare, which is a spin-off from Bell Labs. They had used this in optical cross connects, as they called. It is for fiber optic communication, to move these optical beams coming fiber optic one place to another fiber there, more like a post office for several signals coming through a single fiber. In fact, you can have bunch of fibers. They had these mirrors that I have a video of this and a real prototype to show you how these elastic flexures, rotational hinges were obtained, a bending of the beams. So, here it is just another view of that, but you can look at the animation here, simulation, finite element simulation. So, basically it is a plate that rotates. Now, you can see the tilting of the plate about one axis, and here you can see the tilting about the other axis. So, let us look at a real device that is there now. So, we have this over here, you can rotate like this. If I hold it like this, maybe you can see I can rotate this plate like that, and I can also rotate the other way around. If I hold it like this, I can also rotate this way and that way. I can rotate about this axis like that, I can rotate about this axis, and in fact we have made it in a way that you can see these beams easily, but you do not have to remove all this material. This material can be there, and they can be tiny slots. If you are using silicon etching, you can't see, you will see only a plate, but a center one can rotate about 2 axes. Such flexures also can be done, and people have used a number of designs like this, very ingenious designs that they have. All of these things have one goal, which is to have this multi-axis stiffness here. So, multi-axis stiffness, I think I am not getting the color. Okay, let me see. Yeah. So, we have this multi-axis stiffness, this 6 by 6 matrix. That is, we have translations about x axis, y axis and z axis, and also rotations and corresponding forces and moments. Okay. So, between two relatively rigid bodies, these flexures are giving this multi-axis. All these things differ, as we had noted in the first lecture itself. How these values, cross values, diagonal values, how do they differ? Okay. How do you construct this stiffness matrix, or its inverse, the compliance matrix? How do you do that? To do this, we have to do 6 finite element analysis runs. Today we have finite element, you do not have to go for all these approximate formulae, because they are approximate, but they are useful in design, let us not forget that. But if you want one that you have chosen, everything is fine. Now you want to be very accurate, you can construct these things instantaneously. That is, you take a particular flexure and try to do this. If you want to do that, you have to let us say we take a small length flexure. So, let us say that I have a small beam like this, actually a thin plate. Okay. Let us say that we fix this here, and to this one I attach a rigid body of something, and let us say there is a center of gravity for this, and at that point I apply, let us say, let us choose a coordinate system, let us call this x, y and z. Okay. So, let me just show only the cross section here, it is fixed over there. So, x, y, z. So, now there is a rigid body for this. At the CG of that, let us say apply Fx unit magnitude over there. Okay. Then I get displacements of this thing based on what this flexure's stiffness is. I will get displacements in the x direction, y direction, z direction, rotation about x, rotation about y, rotation about z. All of those I record in a matrix 1, 2, 3, 4, 5, 6. Okay. So, we are not getting stiffness matrix now, actually we get a compliance matrix, meaning that if I put Fx here and then Fy, Fz, Mz, sorry Mx and My and Mz. Okay, what we want are the displacements, that is Ux, Uy, Uz and then theta x, rotation about x axis, rotation about y axis, rotation z axis, right. When I apply unit force in the x direction, one finite element analysis, I get all these numbers, right. I do not have any other forces now, I applied only Fx equal to 1. So, whatever displacements I get from the finite analysis, that will be Ux, Uy, Uz, theta x, theta y, theta z. Then I switch to this and make that unit get the next row, and likewise Fz and Mx. When I say Mx, I have to apply let us say x axis is this way, I have to choose 2 points close by to center of gravity, apply a force above and then another one below, create a rotation about x axis or moment and record all these things. I will get this 6 by 6 matrix. This will be our C matrix, it is relating U to forces. Now, if I take inverse of this C matrix, then I get the stiffness matrix. We can construct that by doing 6 finite element analysis in the present configuration. Let us not forget that in this configuration, after I rotate it by some amount, I have to redo this matrix, because this matrix values in this keep changing, and in fact axis initially may be in fact not maybe, it will be fixed here, but after it rotates a little bit, okay, it will go like this, right. Its distance from here to here will actually change because it is rotating. So, axis is going to drift. So, you have to note down where the axis is, center of rotation is, and what these values are. Each time you do finite element analysis, you can get that. And we have actually done that. I think as a supplement we will put those values for one of these small length flexures and compare with what is out there. You can look at those values, you can do it yourself, you have finite element analysis software with you. And to conclude, before that, let us actually look at some reading that you can do. This classic paper of Paros and Weisbord, I will strongly recommend to you to read how these people had used just simple integration of the beam equation with variable cross section and gave formula that are still used 1965 to now 2016, people still use them. And now this book by Smith and Chetwynd is also quite interesting, because they talk about a lot of this precision mechanism application and focus on the design with all these simple formulae. How do you design, how do you arrange these elements? Some of them are inspired by rigid body linkages, but you can design compliant mechanism very effectively for small range of motion. And this Nicole Le Montio had done this not just for circular cross section, circular notches, but elliptical, hyperbolic and so forth, very painstaking work to derive all these formulae using energy method. And this flexures by S.T. Smith, what called flexures elements of elastic mechanisms. It is also an interesting book which has some overlap with this one, but has very useful information about this conformal method as well. So, what we have discussed in these 2 lectures is how elastic flexures can be used in applications and how we can get the stiffnesses. If we have finite element analysis at your disposal, you can get them very accurately, including the axis drift and axis shifting, not the center moving, but axis itself may be changing. Okay. All of that you can capture, but you have to do for every configuration. What we will discuss next in the next couple of lectures is to use finite element analysis not only to analyze compliant mechanism with elastic pairs or these flexures, but also elastic segments. Then we go towards distributed compliant mechanisms. Thank you.